Okay, in last lecture, we learned about a little bit about plate tectonics and in particular, the plate tectonic setting of Latin America. In this lecture, we're going to build on that to learn more about the geology, the geological evolution of Latin America. So a few acronyms for you. The way geologists talk about time is in billions of years and in millions of years. So rather than writing out 1 billion years ago, geologists will write 1 giga-annum. And instead of just writing 1 giga-annum, we'll write GA. So big G, little a. That means a billion years ago. We will also talk about millions of years ago in terms of a mega-annum, or million of years ago as MA. So keep that in your brain because you're going to see a lot of GAs and MAs in this lecture. So, make this point a little clearer. Earth formed 4.56 billion years ago, or 4.56 GA. Most of the meteorites that fall on Earth are about this age, 4.56 GA. And the oldest rocks on Earth are about 4 billion years old, or 4 GA. Okay, so let's quickly look at the important events in the geologic evolution of Latin America. From oldest to youngest, the oldest, of course, is the formation of the continental crust of what is now South America. And that continental crust didn't all form at 3.5 billion years ago, but the oldest rocks in Latin America are about 3.5 billion years old. And that continental crust formation continued significantly up to the last 500 million years or so. The next thing that happened was the formation of the supercontinent Gondwana. Gondwana, we'll learn more about that. That happened about 600 million years ago. And then the formation of the supercontinent Pangaea, which happened about 300 million years ago. And then Pangaea broke up, and one of the things that reflected that was the opening of the Gulf of Mexico. And that happened about 200 million years ago. And then Gondwana began to break up, and in particular, South America and Africa, which were once together, as you know, opened the South Atlantic, and that began about 120 million years ago, and that continues today. And sort of the last significant geologic evolution in Latin America is the formation of the Caribbean, which is only about 80 million years ago. So here is the geological timescale. You're not going to need to memorize this, but it is useful to know that this is the way geologists divide time. They talk about the Precambrian, and then they talk about the Phanerozoic. And Phanerozoic is the time when we can see evidence of life in the form of fossils. The oldest is the Cambrian time, and the time before that, obviously, is going to be Precambrian. And we can talk about, in Precambrian, we can talk about the Archean, and we can talk about the Proterozoic. We'll go through this, but don't worry too much about these names. So here is the geologic timescale, greatly simplified. The Archean, the Proterozoic, and the Phanerozoic, scaled according to the amount of time in each. And as we said, Earth forms about 4.5 billion years ago. The oldest rocks on Earth are about 4 billion years old. The oldest rocks in South America are about 3.5 billion years old. End of the Archean at 2.5 billion years ago. The oldest rocks in Mexico are about there. And then we have the end of Precambrian time, the formation of Gondwana, the formation of Pangaea, the end of Paleozoic time, the opening of the Atlantic Ocean, and the end of the Mesozoic. So now, one of the things you're going to need to know is that there's 3 kinds of rocks. Most of you know this already. There are igneous rocks, which are rocks that cooled from magma, either coming out of volcanoes, volcanic rocks, which cool the surface, for example, basalt. And there are plutonic rocks. These are igneous rocks that cool at depth, make big crystals. An example of that, of course, is granite. And then hypabyssal rocks. These are rocks that are sort of halfway between volcanic and plutonic. They cool below the surface. Magma cools below the surface, but very shallow depth. So these are the igneous rocks. There's also sedimentary rocks, which are deposited by the action of surface processes. They're the action of water, usually, or wind, and sometimes biological activity to make limestone. And then finally, we have metamorphic rocks. These are heated rocks because they've been buried in the earth. And these are generally sedimentary rocks, but sometimes igneous rocks that have been metamorphosed. So, all right, so here we're looking at the South American geological provinces. And remember, this is the Precambrian, the Proterozoic, and the Archean. Here are the exposures of Precambrian rocks, mostly in Brazil. Most of this over here is Brazil. And then these are covered by younger sediments, Phanerozoic sediments in particular. This light green in here is where the Precambrian rocks are overlain by younger sediments. And then finally is the Andean orogeny, and we'll talk about that. Up here, we're seeing kind of a cross-section of this. So you can see the Precambrian rocks are on the bottom, overlain by sediments in many places. And then the Andean orogeny is over on the east side. So now let's talk about three interesting terms: craton, shield, and platform. So these are all referring to the stable interior of continents where there's not any volcanic activity or significant earthquake activity. So a craton is a piece of ancient crust that's long been stable. And it could be composed of igneous as well as metamorphic rocks. If a craton is exposed to the surface, we have a shield. And if that craton is covered by sediments, we have a platform. So here in Dallas, the oldest rocks underneath us are about a billion or 1.3 billion years old, but they're covered by sediments. So here in Dallas, we're sitting on the platform. Next slide. Okay, so here we've got the South American shields. These are the areas of exposed Precambrian, igneous, and metamorphic rocks. They consist of Archean and older Proterozoic, that's Precambrian, rocks surrounded by younger Proterozoic orogenic belts. And so they're exposed in four places, all east of the Andes. One is the Guiana Shield up here in the north, the Guapore Shield in the west, the São Francisco Craton in the east, and the Rio de la Plata Craton in the south. So here we have it again. And sometimes these are all grouped together as the Amazon Craton. This is the stable continent of South America. So the oldest rocks in Latin America are sitting right about here, just sort of in the northeast corner of Brazil. They're about 3.5 billion years old, or about 3/4 of the age of the Earth. So let's introduce another new term. This is the term orogeny. And orogeny is Greek for birth of mountains. And these are places where new continental crust forms or where old continental crust is deformed by various processes. For example, by continental collision, which we'll talk about. So we can talk about elongate regions of crust affected by the same orogeny are sometimes called orogenic belts or mobile belts. And you may occasionally see a cartoon like this. Subduction leads to orogeny. They are related. All right, let's talk about the South American platform and how it formed. It was assembled when Gondwana began to form at the end of the Precambrian, and sometimes between 550 and 630 million years ago. This is called the Brasiliano orogeny. And basically you took these old cratonic nuclei. Notice here we've got West Africa and Amazonia together. They're not together now. West Africa is obviously in Africa and Amazonia is in South America, and the Rio de la Plata and the São Francisco. And then at 730 million years ago, they were far apart. And as time goes on, they get closer. About 630 million years ago, they collide. And the rest of South America and Africa, for that matter, grow around them. And so these are these Cratons of Africa and South America were together 550 million years ago. So here we are again at the South American platform. You know, we've got our shields, we've got the regions that are Craton overlain by platform sediments. Here we have, again, the South American platform. We talked about this as being the Amazonian Craton too, but where it's overlain by sediments, we should talk about it as the platform. But basically, this is the stable region of South America, where we have thin sediments on top of the Amazonian Craton. And as we said, the Amazonian Craton, the South American platform, is strong. It's not affected by younger deformation. Cenozoic is the last 65 million years. There's really very little folding and faulting in this region. And so the South American platform and the Amazonian Craton basically is everything east of the Andes. So this is the Andes, and all of this is the South American platform. So this is a cross section. This is sort of showing you why these Cratons are strong. It's because they have strong mantle lithosphere. This is maybe 150 kilometers thick. And in fact, there are regions where there's diamonds that are brought up to the surface. We're not going to talk about that in the class, but it actually does happen in South America. But it's this strong lithospheric root of the Amazonian Craton that keeps it stable. All right, now we've got the geology laid out. How does that correspond to the topography? It corresponds extremely well to the topography. The Andes stand out because of these mountainous region on the west side of South America. But the South American platform isn't exactly flat. Here we can see some highlands in Brazil near the coast, the lowlands associated with the Amazon River, slight elevated regions in the north. There is some significant relief, but of course, nothing in the South American platform stands anywhere nearly as high as the mighty Andes. All right, let's revisit this. These words: orogenies, orogenic belts, and orogens. They sound similar, and they are similar, but they are a little bit different. So orogenies are episodes of crustal deformation that generate new crust in mountains and destroy old. So sometimes we talk about the growth of continental crust by addition of material at the margins, but orogenies don't affect Cratons. That's when we start talking about the Andean orogeny, we'll make very clear to note that did not affect the Craton. Similar to orogenies, orogenic belts are elongate zones of high relief and deformation, generally mountain chains like the Andes. The Andes is something of an orogenic belt. And orogens are related to these. They are regions in the crust or crustal tracts that were subjected to an orogeny at about the same time. So these old orogens, some of them can be completely eroded so that there's no relief there. Very old orogens are only identified by the fact that they've got metamorphic and igneous rocks of a certain kind. All right, so here's one example of an orogeny. This is continental collision to form the Himalayas and the Tibetan Plateau. So this is India here, and it has been moving north and colliding with Asia up here. And that collision zone has made the Himalayas here and the Tibetan Plateau back here. And this is the tallest mountain range in the world by far, and the highest plateau. And these are a direct result of this collision of India and Asia by continental collision. Now, the Andes are also a spectacular orogenic belt, and there's lots of volcanic activity in here, as we'll see. there's lots of faulting and there's lots of earthquakes, as we know. Next. So the Andes have been growing over the last 50 million years. And in that time, 350 kilometers or so of crustal shortening and uplift has happened. And so here we are 50 million years ago, and here we are today. And what you can see here is the Nazca plate being subducted beneath the Andes. And this has caused this region to contract, to compress. And you can see that here with these faults. And this region is growing here at 20 million years, and it continues to grow, and it's still growing today. This orogeny is very different than the Himalayan because there's no continental collision. It's only the result of this Pacific oceanic plate subducting underneath the western margin of South America. All right. Now, one of the evidences of the Andean orogeny is the volcanoes. And those volcanoes, as you know, are related to subduction of this plate, the Nazca plate, or the Cocos plate, or the Pacific plate, underneath the western margin at a convergent plate margin. And that causes melting and formation of volcanoes. You would expect that the volcanoes would be almost continuous all along this margin. Wherever there's a convergent plate margin or subduction zone, you expect to be volcanoes. But you see there are gaps here in Argentina and Chile, here in Peru. And in fact, there are volcanoes found in Mexico as well because of that subduction, and over in the Lesser Antilles because this subduction is going on underneath the eastern side of the Caribbean plate. So there have been 319 Latin American volcanoes that are Holocene in age, which means they've erupted in the last 12,000 years. And these are the ones in yellow triangles. There's one there, and there's one there. And there's 63 volcanoes in Latin America are considered to be active. Now, this map is pretty complicated, but it shows ground deformation. A volcano that's likely to erupt is going to show ground deformation. And so those volcanoes in red and blue triangles, those are potentially going to erupt. We don't know when. And then there are some places where satellites have determined there's thermal activity, and those are here. They're kind of hard to see. Now, a lot of information on this slide, but the last thing I want you to notice is the fact that there are volcano observatories that different nations put together to study these. So Argentina has this one, Chile has this one, Bolivia, Peru, Colombia, Ecuador, etc. Obviously, Brazil, Paraguay, Uruguay, they don't need volcano observatories because they don't have any volcanoes. They're on the Craton. All right, so here we have the 4 volcanic zones in the Andes. There's one up here in Colombia and Ecuador called the Northern Volcanic Zone. There is this one in southern Peru, Bolivia, and northern Chile, the Central Volcanic Zone. This one in sort of south central Chile, the Southern Volcanic Zone. And this one down near Tierra del Fuego, the Austral Volcanic Zone. And these are all related to subduction of these plates to the west, from the west to the east. All right, now you'd think, okay, the reason that the Andes are so high is because they're all volcanoes. And many volcanoes are quite high, but not all of the height of the Andes is related to volcanoes. For example, the highest point in South America is Aconcagua, which is a result of compression we talked about. And so you get these kinds of faults where packages of sediments are thrust above each other. We don't need to spend too much time what a thrust fault is, but this is the result of this compression. And all of these are just all the names of the different geologic units. You don't need to know about those. But just, the highest mountain in the Western Hemisphere is Aconcagua at almost 7,000 meters. All right, and many of you may have heard about Machu Picchu. This is the Inca hideout that is now the huge tourist attraction in Peru. This is up in the mountains, up at 9,000 feet or so. Elevation, you can hide things if you put them up in the high mountains. And this was rediscovered in 1911. The Spaniards never found Machu Picchu while they were occupying the colonies, but they suspected that it existed. And it was occupied for about 40 years after the Spanish took Cusco in 1533. And interestingly enough, geologically, the rocks that it's built on are 246 million year old granite. It's not a volcano. All right. This takes us to Latin America and the supercontinent cycle. Now, this word is an interesting word because it implies two things. One is there's such a thing as a supercontinent, and the other is there's some kind of a cyclic appearance and disappearance of these things. And that, in fact, is true. The supercontinent cycle refers to the episodic aggregation and dispersal of continental crust. And we'll talk a little bit more about what that means. And the supercontinents form when most of the continental crust is found in a single large mass, a single supercontinent. And of course, if there's only one continent, then there's only going to be one ocean, right? So that would be a superocean. And supercontinents form as a result of a protracted period of continent-continent collisions associated with plate tectonics. Typically, it takes about 300 to 400 million years for one supercontinent to form, break up, and form the next one. And there's three important supercontinents we'll talk about. One formed about 200 million years ago. Before that one, about 600 million years ago. And before that, about 1,000 million years ago. We may not say much about that. Okay, so the supercontinent cycle is related to a thing called the Wilson cycle. And the Wilson cycle is more about the oceans. The Wilson cycle is the opening and closing of new oceans. So here we have, let's say, a continent, and it's rifting, and that rift opens into an ocean, and that eventually, that ocean eventually closes and collides and makes a new continent. So that's the Wilson cycle, opening and closing of new oceans. The supercontinent cycle is analogous to that. It's complementary to that because it's about the formation and destruction of supercontinents. So here we've got the Pangea supercontinent, and then it breaks up to form a new ocean. This is the rifting up here off the coast, east coast of North America to open that part of the Atlantic. And then we get this situation today. So this Wilson cycle and supercontinent cycle go together. So this is the most recent supercontinent called Pangea, all Earth. So this is about 200 million years ago, and we put on all of the nations of the world today. We're here in the United States, but what you see is, South America is here, and Africa is here, and Antarctica, India, and Australia are here. Basically, we've got all of this, the continents are all together in a single Pangean Earth. All right, so Pangea formed about 300 million years ago when Laurasia, which is the northern continents now, so that's North America, this is Asia, collided with the southern continents, which is Gondwana, South America, Africa, India, and that made a collision zone that came through here, an orogeny. So here is a geologic map of Gondwana, and what we're seeing here are the geology geologic units. You can see the shields here, the Guyana Shield, the South and Brazilian shields here. Here are some shields in Africa, in India. And so basically, this is all of these continents that have been put back together as they existed about 200 million years ago. And so we talked about the fact that these Cratons, the Amazonian Craton was part of the West African Craton. The Sao Francisco Craton is part of the Congo Craton, Rio de la Plata. So these Cratons were all together when they were in Gondwana. Now they're quite separate. So here we can see the Pangaea that existed 225 million years ago. So this is Laurasia in the north, Gondwana in the south, and then they break up in the Triassic. You notice that South America and Africa stay together as recently as 135 million years ago, and then but they start to break up about 100 million years ago or so. And today we're seeing all of the continents moving farther away. But basically, Pangaea, this supercontinent, is equal to Laurasia and Gondwana put together. All right, now we're going to watch a reconstruction. First, we're going to show you the present Earth, and they're going to go back 200 million years ago and come forward and show you how the continents moved. All right, so when we break up a continent and make a new ocean, we make something called a passive margin. So passive margin is contrasted with an active margin. So the active margins are the plate tectonic margins, which, as you recall, are divergent plate margins, convergent plate margins, and transform margins. These passive margins are not plate tectonic margins. They are margins between different types of crust. Remember, continental crust is thick, oceanic crust is thin, and where they come together, you've got a region that has a lot of geologic changes. And the way these passive margins form is by rifting of the continent, and as that rifted zone ages, it cools, it subsides, and sediments derived from the continent tend to get deposited there. So you get big, thick sequences of sediments on these passive margins. And we'll find out that this is just as important to the nations of Eastern Latin America, especially Brazil, as it is, as ore deposits are to the nations of Western Latin America. They have ore deposits, but the Eastern nations have oil, mostly in these passive margin sedimentary accumulations. So now let's watch a video of and a little bit more about how continents rift, form new oceans, and also passive continental margins.
Rifting is the process of stretching and thinning of a continental plate, caused when a single plate starts to break apart into two plates. Rifting sometimes evolves into seafloor spreading. Rifts also provide sites where great thicknesses of sediment can be deposited. If rifting evolves to seafloor spreading, great sedimentary basins known as passive continental margins will form between the ruptured continent and the new ocean. Passive continental margins are great places for major seaports and cities and provide favorite destinations for summer vacations. This video explains all of these things and more. Rifting affects the continental lithosphere. Continental lithosphere consists of the continental crust and the uppermost mantle, which together forms the strong outer shell of the Earth, extending to about 100 to 200 kilometers deep. There is both oceanic and continental lithosphere, and these are the plates of plate tectonics. We say that the lithosphere is rigid because when a strong force pushes or pulls on it, the lithosphere will break. The lithosphere rides on hot, weak asthenosphere, and this makes plate tectonics possible. We say that the asthenosphere behaves plastically because when a force is applied, the asthenosphere will flow or convect, similar to boiling water or the rising blobs in a lava lamp, but much more slowly. The process of starting to pull the lithosphere apart is called rifting. As rifting progresses, the lithosphere thins more and more, allowing the underlying asthenosphere to rise and melt to form magmas that rise to the surface and erupt as lava flows. Good examples of continental rifts are found in the East African Rift, the Rhine-Graben of Germany, and the Rio Grande Rift of New Mexico in the United States. Over time, the lithosphere may thin completely, allowing the asthenosphere to reach the surface. When this happens, seafloor spreading begins, and the single plate becomes two smaller plates. This is what happened when the Red Sea formed, separating the African and Arabian plates. Volcanic eruptions are common during the early stages of rifting. As lithospheric extension progresses, the rifted region sinks or subsides. Sediments are also deposited in the subsiding region, so interbedded terrestrial sediments and lava flows are common in early rift deposits. The more the lithosphere is stretched, the more it subsides. Eventually, the surface of the rift lies below sea level, allowing the sea to invade to form a young ocean like the Red Sea. Sometimes the young ocean may be repeatedly blocked from the sea, allowing the seawater to evaporate and leave behind evaporite deposits such as halite and gypsum. Once the lithosphere has thinned completely, seafloor spreading will begin, and the young ocean will widen enough to make it impossible to block seawater from the larger ocean, ending evaporite deposition. Normal marine sediments, such as limestone and shale, are then deposited as an open seaway is established. Thus, in the evolution of a continental rift widening into an ocean, the sequence of terrestrial sediments and lava, overlain by evaporites, overlain by marine sediments, is expected. Once the lithosphere thins completely, allowing the asthenosphere to reach the surface, seafloor spreading begins, breaking the original one plate into two plates. The young ocean progressively widens with time once seafloor spreading begins. At the same time, the two halves of the original rift subside to become passive continental margins. Passive continental margins are not plate boundaries, but are the two separated halves of where the new plate boundary began to form as a continental rift. Passive continental margins mark boundaries between continental and oceanic crust. Passive continental margins lie beneath continental shelves and coastal plains, like those of the eastern United States and around the Gulf of Mexico. Because rivers flow from continental interiors to the sea, passive continental margins accumulate unusually thick deposits of sediments. These exhibit a sequence of terrestrial sediments and lava, overlain by evaporites, overlain by marine sediments. As seafloor spreading continues, the two halves of the rift, now passive continental margins, are increasingly separated with time. An example of this is seen in the passive margins of the eastern United States and northwest Africa, which once were part of a single plate but were separated beginning in Jurassic time. Today, the two halves of the ancient plate are separated by the Atlantic Ocean, which started as a continental rift. Passive continental margins are natural places for seaports, many of which have grown into bustling seaports, like New York City, Houston, London, Bombay, Calcutta, Singapore, Hong Kong, Shanghai. The huge piles of sediment in passive continental margins are also important because they host many deposits of oil and natural gas. We hope this overview of continental rifting, young oceans, and passive continental margins and how these are related has been informative. The next time you enjoy a day at the beach, take a moment to think about the plate tectonic processes that created your vacation spot.
So here are the passive margins of the world. You notice the big difference between the Pacific over here and the Atlantic is an ocean that's surrounded by passive margins, and the Pacific is one that's not. In fact, this, as you know, is the circum-Pacific ring of fire related to the convergent plate boundaries there. But it's one of the ways that those two oceans are very, very different. And you see that here in Latin America with these, broad region of passive margins on the eastern side of South America. Next slide. All right. So, as we said, the breakup of Gondwana produced these passive margins on the flanks of the rifted continents, facing the newly formed Atlantic Ocean. And that offshore Brazil is now a major oil producing region. This is very important to the economy of Brazil. And what you can see is that Brazil has been increasing its oil production from these reservoirs. Here's the United States, this region. Brazil is showing tremendous growth in the amount of oil it's producing. All right. Now, we also have a bit of a passive margin up here in the northern part of Latin America. Here we are in Texas. All of this is a passive continental margin, all the way around the Gulf of Mexico. And so eastern side of Mexico is a passive continental margin. And unsurprisingly, it has very significant oil deposits as well. All right. Now, one of the things that happened is the Gulf of Mexico opened and Mexico was assembled by some very interesting tectonics. So here we are about 175 million years ago. And what we're seeing here is a funny map, but it gets the point. Here we have South America. This is the northern part of South America. This is the West Africa. There's Florida, the Gulf Mexico states down to Texas. But Mexico looks like it needs to be put back together. And in fact, that is what geoscientists think happened, is this opening of the Gulf of Mexico in here caused a lot of strike-slip faulting that basically slid Mexico into place, and for that matter, Central America. It's one of the most interesting geological episodes in American geology history. All right, now here is a passive margin in the making. This is the Gulf of California. So California is up here, Baja California is this peninsula. And this region in here is the Gulf of California, sometimes called the Sea of Cortez, off the west coast of Mexico. And this is the East Pacific Rise is spreading here like this. And what you see here, up here in the north is the San Andreas Fault. It's quite famous, strike-slip fault, transform plate boundary with, the west side is going that way relative to the east side. And the Gulf of California is little spreading segments, little divergent plate boundaries offset by long transforms. There's another little spreading segment like that. And that is slowly taking Baja California and everything in California west of the San Andreas Fault northwards. So this is making a passive continental margin in this region. Just getting started, because it only happened about 5 million years ago. Now let's look at a short video about the opening of the South Atlantic. Okay, now another very interesting geological aspect of Latin America is the Caribbean. The Caribbean is really an unusual place because it is a sea surrounded by islands. You know, here we've got small islands, and then they come around here, they get bigger and bigger to Cuba. And all of this in here, the Caribbean, is enclosed in these island chains. How did that come to be? So let's watch a very short video that will explain it to you. Basically, the Caribbean rafted in from the Pacific and was caught between North and South America.
vuelta pa' aquí, otra vuelta pa' allá, cosa buena. El son del martillito es un baile popular, tú verás. Se baila muy despacito, por Dios, es algo muy singular, mi negrón. Ay, mira mi nena buena, por Dios.
All right, so we have covered in very quickly the important events in the geological evolution of Latin America. And that we talked about the formation of the continental crust in South America, beginning at 3.5 billion years ago and continuing up to about 500,000 years ago. Then the formation of the supercontinent Gondwana about 600 million years ago. Then the formation of the supercontinent Pangaea by colliding with the northern continents about 300 million years ago. And then the breakup of Pangaea and the opening of the Gulf of Mexico about 200 million years ago. The breakup of Gondwana and the opening of the South Atlantic about 120 million years ago. And then most recently, the formation of the Caribbean. Now, we could also add in here the evolution of the Andes, which is started much more recently and continues today, but we'll leave it like this.